So we want to graph the rational function r of x equals x squared plus 8x plus 15 divided by x plus 5. So again, we have to go through these steps that we talked about when analyzing a rational function. So our first step is to factor this and figure out its domain. So if we factor the numerator factors to be x plus 5 times x plus 3, and then the denominator doesn't factor, it's just x plus 5. So that's the factored form. We know that the denominator gives us a domain restriction, right? So we know that x plus 5 cannot equal 0, which means that x is not allowed to equal negative 5. So our domain is the set of all x such that x does not equal negative 5. And then in interval notation, that would be from negative infinity to negative 5, union from negative 5 to positive infinity. Next, we want to write this in lowest terms. So lowest terms means that we would reduce any factors that are in common in the numerator and denominator. And we actually see that there's an x plus 5, a factor of x plus 5 in common in both of these. So now we have our function, and our function in lowest terms is going to be acting like just this linear equation, y equals x plus 3. So that's our lowest term of our rational function. So let's find the x and y intercepts. So remember that x-intercepts occur when we make the y value 0. So we have 0 equals x plus 3. So subtract 3 and we get that x is equal to negative 3. So we have an x-intercept at negative 3, 0. And then y-intercepts occur when we make the y value, or sorry, the x value 0. So we have y equals 0 plus 3. So we have y equals 3. So we have a y-intercept at 0, 3. Vertical asymptotes. So remember, vertical asymptotes come from domain restrictions. But because our only domain restriction, this one here, is one that can be removed, right? When we simplified it, it went away. That actually doesn't give us a vertical asymptote. That's going to give us a hole. So there's actually no vertical asymptote. There is no vertical asymptote, but we will have a hole. So this is like a added bonus at negative 5, comma, something. Now to figure out what this value is going to be, we just take negative 5 and we plug it into our reduced polynomial, or into our reduced rational function. So the rational function in lowest terms, plug in a negative 5. So negative 5 plus 3 is negative 2. So there's going to be a hole at negative 5, negative 2. And that came because there's no vertical asymptote, because this domain restriction was eliminated when we put it in its lowest term. The horizontal asymptote, so this is over 1, right? We can imagine this being over 1. So the numerator's degree is larger than the denominator's degree. So that means there are no horizontal asymptotes, but possible oblique asymptotes. And actually, there is an oblique asymptote, and the oblique asymptote is actually just our graph. The entire graph itself is an oblique asymptote because it's just this line, right? So that is an oblique asymptote technically. So let's graph this. This one says that you should go to a graphing utility, or normally that's what we would do, but I actually don't think we need it for this problem because it's just a line. Now we know that there's a hole at negative 5, negative 2. So negative 5, negative 2, there's going to be a hole here. And we know that there are intercepts. We have an x-intercept at negative 3, 0. We have a y-intercept at 0, 3. And if we wanted to graph this function, we know that this has a slope of 1. So we could go up 1, right 1, or down 1, left 1, and continue to get more points. But really all we need is 2 points, and then we can draw our line. So this graph should go through all of these points. And it goes on forever in this direction. And then it also is going to go through all of these points down here to give us the other half. So this is our graph there. So it just looks like a line, but it has a hole here at -5, -2. And then we had our x-intercept here at -3, 0. And we had our y-intercept here at 0, 3.